Hello everyone, welcome to the control systems. This is part 3 of lecture 9, root locus techniques, and in this section we'll discuss root locus sketchings by hand. There are some certain rules that you need to follow to sketch the root locus, and you read some textbook they say 5, and some textbook they say 7, and some textbook there are 10s. So it doesn't matter as long as it works for you. You can follow the textbooks. In in this lecture, we'll consider a 7 rule to sketch a root locus. So, for example, rule number 1, it's about number of branches. So it is stated that the number of branches of root locus equal to the number of branches of the closed loop poles. So if the pole have, if there are 2 poles and then there are 2 branches, okay, consider like for example like this. The crosshair is the notation for the poles. So there are 2 poles, and as you can see, there are 2 branches. Okay. We will get back to how to sketch later. But now, rule number 1 states that the number of branches of the root locus equal the number of branches of the closed loop pole. And rule number 2 is about symmetry. So the root locus is symmetrical about the real axis. Okay, it's very obvious. And rule number 3 is all about real axis segments. Okay. On the real axis, for k larger than 0, the root locus exists to the left of an odd number of the real axis. Finite open loop pole and or finite open loop zeros. Okay, so the root exists to the left of an odd number. For example, you can label it 1, 2, 3, 4, and then this is an odd number to the left. I mean in this interval. This is so 1, 2, 3, and this is an odd number and to the left. So it exists in this interval and this interval. And rule number 4, it's about starting and ending points. Okay, so the root locus, it is stated that the root locus begins at the finite and infinite poles of GS or HS and end at the finite and infinite zero of this GS times HS. So now consider the closed loop transfer function given by this functions. And then if k approach 0, it means small gain. If k approach 0, and then this k approach 0, so this term will be very small. Okay, and this d is denominator of GS and HS. And we conclude that the root locus begin at the pole of GS and HS. I mean the denominators. Okay, when k approach 0. And when k approach infinity, this term will be dominant. Okay, dominance. And then this you can assume to be very small because this term is already dominant. And then, as you can see in this term, we can conclude that the root locus end at 0 of GS times HS, which is this definition. So again, the root locus begin at the finite and infinite finite and infinite poles of this, and end at the finite and infinite zero. Okay? So end it means when k approach infinity. And rule number 5 is about behavior at infinity. So we considered applying the rule number 4 to the following open loop transfer function. There are three finite poles. Uh, this s equals 0, s equals minus 1, s equals minus 2, and there's no finite zeros. You can see here, finite 0, no finite 0. However, the functions can also have the infinite pole and 0. In this case, it exists infinite 0. No, there is no finite 0, but it exists infinite 0. This is something that we also need to remember. If the function approach infinity as s approach infinity, and then the function have the pole at infinities. Okay, and if the function approach 0 as s approach infinity, then the function has 0 at infinities. For example, if we have gs equal s, has a finite pole at infinity, because when gs approach infinity, because gs approach infinity as s approach infinity. On the other hand, this function gs equal 1 over s has 0 at infinity, since this approach 0 as s approach infinity. And every function of s have an equal number of pole and 0. Okay, if we include the infinite poles and 0, as well as the infinite poles and 0, as well as the finite pole and 0. So it has equal number of poles and 0. And for illustration, let's consider this kgs and hs, approximately k over k over s power by 3, given like this. So each s has the denominator causes the open loop function to become 0 as s approach infinity. So you can conclude that it has 3 0 at infinity. So the root locus begin at the finite poles and end at the finite infinite 0. Okay? But where are the infinite zeros? And there are some rules that you can sketch, not some rule, it's rule number 5 actually. You can sketch and then you can graphically see where is the infinite 0 pole. So the root locus approach straight line as asymptote as the locus approaches infinity. And the equation of the asymptote is given by the real axis intercept, this one, which is given by this, and also the angles, okay, given by this ones. So the angle is in radians. For example, consider this system with negative feedback, and then you can compute the real axis intercept using these formulas. The sum of finite poles minus sum of finite 0 over number of finite pole minus number of finite 0. Okay, this is the poles, the 0, and this is the number of pole minus the number of 0. So the real axis intercept is at minus 4 over 3. And also the angle can be computed. Okay, you can give k equals 0, k equals 1, k equals 3. And this is graphical representations. Okay, so we have 4 poles, 1, 2, 3, 4, this is finite pole, and this is finite zero, and then this is asymptote. Okay, so the intercept at this point. So it's begin at the pole, and you need to use the previous rule. For example, you know that there exists a root local at this interval, at this interval, at this interval, and it begin at the pole and end up at zero. So if they exist at this interval, so it have to come to this direction, and using this asymptote, so okay, go in these directions. This is obvious. It from the pole, begin at the pole and end at the zero, and this is the pole and zero. So there's an infinite zero here. And rule number 6 is about real axis break-in and breakaway point. So real axis, it means it lie on the x-axis. You want to know where is the break-in and breakaway point. So for each s equal this sigma on the real axis segment of the root locus, you can just substitute this value into the these functions. Okay, remember that the denominator equals 0, so 1 plus k g s h s equals 0. Substitute alpha in, sigma in the equations, and then you do the derivative with respect to this sigma and equate it to 0. So for example, you have this function defined like this, and substitute this sigma in to the derivative with respect to this sigma and equate it to 0. So you will obtain this sigma 1 and sigma 2, which are the breakaway and break-in point. Okay, so this point and this point. Okay, so this is breakaway, this is break-in. And rule number 7 is the j omega axis crossings. So it means it cross this j omega. Okay, cross the imaginary axis. So if s equals j omega is a closed loop pole on the imaginary axis, then it satisfies this equation. Okay, consider again these functions, and you can just substitute this s into this function. So you will have this equation. Okay, you can combine the real part in imaginary part and then solve for these equations. Okay, equal to 0, and this is the real part, and this is the imaginary part, also equal to 0. This is 0 plus I plus j 0. Okay, and well, you just do the math and then you can find k. Okay, there are two k here, and this got the negative 1. Okay, since this is a negative feedback, k should be larger than 0. Thus, you can find k and you can find omega. Okay, thank you for watching this video.